Yeah, as we discussed earlier, the third moment is what is the measure of symmetricity in the data. See, when we look at the data, the first one is saying what is the center value. The second one is saying how much is the data spread. And now my third aspect which I require is, okay, data is spread. But is it equally spread towards the left of the mean as well as right of the mean? Towards the lower side and higher side, is it evenly spread? I know there is a standard deviation, means there is some dispersion in the data. But is the dispersion, so this is the center, this is the deviation. I know that the deviation, on an average, the deviation is this much. But on an average is always a tempting word, right? The deviation on an average is this much. Is it same on both sides? Or is the deviation very heavy on this side, but very light on this side? Very less deviation from the mean on the right, but very large deviation on the left. But still the average could be the standard deviation, right? Let's say if one value is deviating, let's say this is the mean. I have one value something here. The deviation of this is very large, right? Whereas here, let's say I have 5 values here. All 5 of them are having very less deviations towards the right. Now, the average deviation is what we are talking of as standard deviation or the variance. So that average deviation may be somewhere in the middle of these two. Now, the average deviation is something, but what we are seeing is to the right of it, the deviations are much lesser, but to the left of it, the deviations are much higher, right? Because we do a squaring, we don't know whether the deviations are more towards the left or towards the right. So I need something which will actually give a positive as well as a negative value to understand the pattern in the deviation. If the deviations are uniform both to the left as well as to the right, I call that as a symmetrical. But if it is more to the left and less to the right, or more to the right and less to the left, we say that there is some level of skewness present in the data, right? So based on that, so probably a normal distribution is more like a symmetric distribution, but a chi-square distribution is more like a right skewed distribution. There's so much of deviation towards the right, right? So that's where we call as a right skewed or positively skewed kind of a distribution. There could be some other distributions which are left skewed kind of distributions. So there are some deviations to the extreme left. Deviation is nothing but some value is there to the extreme left. The deviation is very high from the mean. So by understanding the characteristics of the data, is it more symmetrical or is it more skewed, we can apply the appropriate statistical and the probability distribution to that particular data. So as it is mentioning, these are the 3 types of data which we can observe. This is nothing but I take the frequency distribution of each of the data. The frequency and the mean. The class interval or the value and the frequency. Try to join the points like a histogram or something. The shape of the histogram, if it looks more or less uniform on both sides, we call it symmetrical. The shape of the histogram, if it looks more towards the right, which means there are so many, it's like this, okay? The histogram may look something like this. So if I try to join the points, it's nothing but it comes like this, right? So this is like a right skewed, which means there are some extreme outliers to the right. But if the histogram is having more or less a symmetrical kind of a structure, we say that that data is following a symmetrical pattern about the mean, right? So, and similarly, the negatively skewed. The way we compute it mathematically, we can look at it through the histogram just by plotting a histogram or a stem and leaf plot or a dot plot, any plot. Because in stem and leaf plot also, if I see more values in the first two rows, just look at it like this. More values in the first two rows, and then it decreases. Try to tilt it, even that is a right skewed kind of a distribution. Try to tilt the graph by 90 degrees, you will see that there is a kind of a right skewed kind of a distribution. But on the other side, let's say your stem and leaf plot, it is like this. If it is something like this, it is looking more like a symmetrical. If we are trying to plot, if you are trying to tilt the graph and trying to join the high points, it is coming more like this. So there is a kind of a symmetric nature in that graph. So the more symmetrical you are able to see, you can see from the stem and leaf. You just tilt the graph. You just tilt the graph, you will see whether it is more symmetrical or more skewed towards the right like this, positively skewed or right skewed, more skewed towards the left like this, negatively skewed or left skewed. Because this is on the positive side, it is getting dragged towards the positive side. Typically on the plotting also, towards the right we call as the positive x-axis, and towards the left we call negative x-axis. So if the data is getting dragged towards the right, we are calling it as right skewed or positive skewed. Data is getting dragged towards the left, which means this is nothing but a frequency distribution here means it's nothing but you have a histogram coming up even here also, like this. There is a histogram that is coming up here, which means there are some values even at this value of x. So there are some extreme left values, which are like extreme outliers on the lower side. So when the graph is more positively skewed, we say outliers are on the higher side. Higher side means very big values are there. 1, 2, 3, 4, 5, 100. There is some 100 in the data which is pulling towards the right. Whereas when we are saying negatively skewed, my data would be like this: 1, 2, 3, 4, 5 and minus 100. There is one very low value which is pulling my data towards my left. My graph is getting pulled towards the left because the histogram is present somewhere even for a very low value also. That's the reason my graph is coming that side. But if it is more symmetrical, yeah, there are equally distributed on both left hand side as well as the right hand side. So that's the reason when we calculate also, we calculate it as a third central moment. Central moment is nothing but with respect to 0. Central moment is with respect to mean. Mean, x minus x bar whole cube. Center is nothing but the mean. Origin is 0. Central is with respect to mean. So the way we calculate it is xi minus x bar whole cube sigma, and we do 1 by 2. This is the definition of skewness. And if the data is symmetrical, the skewness will come out to 0. Very, very close to 0 it should be if the data is symmetrical. Now let's say on the data itself, if you have to apply it, okay, on this data itself, let's say if I have to apply it, let's see on this data, which is nothing but The mean of this data, is 37.3. Now what I am doing, every value I subtract the mean and do a cubing. X minus x bar whole cube. X minus x bar whole cube is this one. And let's say I take the average of that. Now this is the x minus x bar whole cube and a sigma. Now if I take the addition of all of them, because sigma has to be done, sigma of all of them divided by n, 20. This is what is giving me my skewness. Skewness is minus 444 here, which means there is a negative skewness. So there is some data which is on the extreme left of it. The skewness is towards the left hand side of the data, right? So even if we see here, there is something. See here, you see 20, almost 17 units away from the mean. Whereas on the higher side, there is 49, only 11 units or 12 units away from the mean. So it's not uniformly distributed on both the sides. There are some extreme left values, right? You see 20, 21, these are much away from the mean compared to the right side. So that is what is a measure of skewness for us. If it is negative, we say that the data is negatively skewed. If it is positive, we say it is positively skewed. But in most of the cases, for our finance related applications or for insurance related applications, we see that the data is more positively skewed itself. Almost a good number of distributions which we talk about, we hardly have many negative distributions at all for us. Whether we talk about Poisson distribution or chi-square distribution or exponential distribution, there are so many distributions which are purely positively skewed distributions only. We don't have many negatively skewed distributions as far as our finance or insurance kind of a data is concerned. So this is the way we calculate the skewness. Because it's a cube, the value can come out to be positive or negative. Positive skewness means we say that the tail is long on the right. Negative skew means tail is long on the left. And now here we got 444 or something in our data. I don't know whether that is very high or very low. There is no way, there are no boundaries to that value. I don't know whether it is very high or very low. From that standpoint, people wanted to talk about bringing some kind of consistency so that they can explain it better. Is it very high? Is it very low? Because minus 444, I'll say it is relative to the data. Or minus 444, it will be based on in some units. If that x, if all the 20 values are centimeters, my skewness is also minus 444 centimeter cube, cubic centimeters, because it's a cubed quantity. So people wanted to make skewness dimensionless. So for that, what they have done is, whatever we got through the skewness earlier, some normalization is happening on that. What is that normalization? You take the second moment, or simple way of talking about is you take the standard deviation cube. You divide it by the standard deviation cube. Whatever the skewness you got, you divide it by the standard deviation cube. That is what we are calling it as coefficient of skewness. Skewness is different, coefficient of skewness is different. Coefficient of skewness is a dimensionless quantity because you are dividing by some other cube. You are dividing it by some other cube. Cube by cube, the units are getting cancelled off. Only the value will get retained. So that is where we are dividing. In our earlier answer, whatever the 444 we have got, this is typically divided by the standard deviation Q. So minus 0.61 is the skewness, because how far is it away from 0? Minus 444, the moment I see, it looks as if it is very much away from 0. So they wanted a normalized kind of a value which says, is it very much away, which can be comparable between the data sets. Right? This process is done just to compare two data sets. Okay, minus 440, if instead of 20 values in this data, if I have 200 values, my skewness would have been minus 20,000. For this normal skewness itself would have been, let's say, minus 20,000. Now that will say the skewness is very, very high. But that is high because the data is very large. So I want some kind of a normalization in my skewness. The normalization in the skewness is done by dividing it by some other adjustment factor, which is a dimensionless quantity for me. So I'm making it minus 0.61. In this case, yeah, it is around, it's somewhere close to 0, but slightly away from 0. Right? So generally, I mean, again, this need not be looked at from an exam standpoint. Practically, when we are working it, we even say, okay, as long as it is minus 0.3, minus 0.4 to plus 0.3 or plus 0.4, we will assume it to be 0 itself. Because exact zeros are not possible. We are not working on adjusted data. We are working on real data in practical world. So anything close to this minus 0.3 or plus 0.3 kind of numbers, still we can take them as zeros itself, saying the data is more or less normal, more or less symmetrical. Right? So that is the way we measure the coefficient of skewness, and the most commonly used. Rather than using skewness, people use coefficient of skewness very effectively, because even the tools like Excel, they do the calculation for coefficient of skewness in a very straightforward way. There is a formula called skew in Excel, which will actually give the coefficient of skewness directly. Minus 0.71, some calculation things here. Minus 0.71 is the coefficient of skewness from this data, which is directly being given by tools like Excel. They don't give skewness. They only give coefficient of skewness, because that is the one which can be comparable between the two data sets. Right? Here actually the formula issue. If I directly do with x1 minus x bar, see here also they do some kind of sample. I mean, the calculation which Excel does is slightly different. Let me just look at it. There's a small difference, but the way it works out is you divide it. See, actually you don't divide by standard deviation cube. You take the second moment, which is, see, in a sample we divide it by n minus 1, but in these calculations we divide by n. We don't divide by n minus 1. That's where that small difference comes up. But in a very broad sense, to understand the coefficient of skewness, it is nothing but the skewness value, whatever we get, we divide it by the second moment to the power 3 by 2 or standard deviation to the power 3. Then one more thing people will do typically in assessing the data, especially even including the 3, the box plot, the advantage is it is helpful in finding out both the mean, the standard deviation, and or probably the central tendency, the dispersion, as well as skewness in the data. This is one simple diagram which can help us in finding out all the 3. The simple way to look at is, the way it is plotted is Q1, Q3. There is a box that is created with Q1 on one end, Q3 value on the other end. The median is plotted somewhere in the middle, and the lower values, because Q1 will divide it into 25% of the values will be towards the left of it. So the lower values, and probably this is my minimum, and these are the higher values. This is my maximum, and this is what is called as a box plot. And here what we can simply see is, this is a measure of central tendency. Median is a measure of central tendency. This is a measure of dispersion, interquartile range. Interquartile range is a measure of dispersion, and I can very well see whether the tails are equally distributed to both sides, or big tail on the left or big tail on the right. So if this tail size is more or less similar on both sides, I say it is close to symmetrical. If it is if it is more like this, the tail is smaller this side, but it is very larger this side, I can say that there is a right skew or a positive skew in the data, or the left skew or negative skew in the data. So this actually, when a tool like SPSS or any other statistical tools, they plot this kind of a box plot, what they also do is they identify some stars. Stars are nothing but the outliers in the data. Any box plot you plot using a tool, they identify the ones which are outliers, which don't behave just like any other data in the data, which are quite away from the other set. Those are all treated as outliers, and all those outliers are plotted with stars. And it's an advice always, whenever we are working on any kind of a data, we remove the outliers and again redo the entire process. That, because for us the major thing in any statistical analysis is establish a pattern. One or two outliers, they deviate our pattern altogether. They disturb our pattern altogether. So it's better to remove them and then re-establish the pattern whenever we are trying to compare two data sets. So that is this is one of the tools which is a very important tool to understand, especially all the three things in the data: the central tendency through the median, the dispersion through the interquartile range, and the skewness through the ends. The ends are also called as whiskers. So that's where this graph is called as box and whisker diagram, or a typical name is box plot for it. Right?